Welcome to a completely different world of data management. We are entering the realm of NoSQL databases with MongoDB. MongoDB is the leading document database, offering flexibility and scalability that relational databases, like MySQL and PostgreSQL, may not easily match. 1. What is NoSQL and MongoDB? NoSQL stands for Not Only SQL. These databases handle unstructured or semi-structured data and do not rely on fixed table schemas. MongoDB specifically stores data in flexible JSON-like structures called documents. 2. Core concepts, documents, and collections. Think of MongoDB concepts by comparing them to relational databases. A document is the equivalent of a row in a table. A document is simply a map of keys and values, similar to a Python dictionary. A collection is the equivalent of a table, holding a group of related documents. Crucially, documents in the same collection do not have to share the same fields, making the schema highly flexible. Here is an example of a MongoDB document. Notice the nested fields, like supplier, and the list of values, tag. This kind of complex data can be stored naturally within a single document, simplifying data access. 3. Section roadmap. To work with MongoDB, we will first install the server. Then we will explore the MongoDB console before installing the Python connector, pymongo. Finally, we will cover all the CRUD operations using the pymongo API. To summarize, we are ready to dive into the flexible world of MongoDB. Our next lecture 30.02, Install Mongo. See you there. Welcome back. Before connecting from Python, let us spend a few minutes in the MongoDB shell. This helps us understand the structure of MongoDB commands, which are very different from SQL. 1. Accessing the Mongo SH. Two. Basic database commands. The command to view existing databases is show DBS. To switch to or create a new database, you use the used command. Let us switch to a new database called MongoDB_Python, which MongoDB creates if it does not exist. Three. Inserting a document. To insert data, we access the current database using the db variable, then specify the collection name, for example, db.customers, and call the insert1 method. The argument is the document itself, written in JSON format. For finding data. To perform a read operation, we use the find method on the collection, calling db.customers.find, parenthesis without any arguments retrieves all documents in that collection. We now have a basic understanding of MongoDB's syntax. To summarize, you now have a foundational understanding of MongoDB commands. Next, we install the necessary Python connector so we can execute these types of commands directly from our Python scripts. Our next lecture 30.04, Install pymongo. See you there. Welcome back. The MongoDB server is running, and you have seen the Mongo shell. Now, let us install the Python library we will use to connect to and interact with MongoDB, pymongo. 1. Introducing pymongo. pymongo is the official and recommended Python driver for MongoDB. Its primary job is seamless translation. It automatically converts Python dictionaries into BSON, or binary JSON, format, which is how MongoDB stores its documents. This makes working with MongoDB feel very natural in Python. 2. Installation command. Open your terminal and use the pip3 command. There is no special binary version needed this time. Simply type pip3 install pymongo and let it finish the installation. 3. Verifying the installation. Just like any other library, you verify the installation by running a small script or entering the Python interpreter and attempting to import pymongo. If the import passes without error, you are ready to connect to the MongoDB server. To summarize, the bridge between Python and MongoDB is complete. Our next lecture 30.05, PI walkthrough. See you there. Welcome back. Before we start inserting data, we must understand the three core objects in the pymongo API: the client, the database, and the collection. These objects form a clear hierarchy that defines how we interact with MongoDB. 1. The Mongo client is the top-level object. It is responsible for establishing and managing the connection to your MongoDB server. We create an instance of Mongo client by providing the server's URI or URL, which for our local installation is the default address. The code uses Mongo client and the URI string. Once this line executes, the client is ready to access databases. Note that MongoDB does not require explicit connection closing, but it is good practice. 2. Accessing the database. The second level is the database. Unlike SQL databases, MongoDB databases do not need to be created upfront. They are created automatically when you first insert data into them. We access a database object from the client using simple dictionary-style bracket notation or dot notation. Both dot notation, client.mongodb_python, and bracket notation, client bracket quote mongodb_python quote bracket, retrieve the database object. We will store this in the DB variable. 3. Accessing the collection. The third level is the collection, which holds the documents. We access a collection object from the database object using the same dictionary style or dot notation. This is the object where we will execute all our CRUD methods, like insert1 and find. We will be working primarily with this collection object in the upcoming lessons. To summarize, you understand the pymongo API structure. We are now ready to perform our first write operation. Our next lecture 30.06, insert 1. See you there. Welcome back. Having set up the pymongo connection hierarchy, we can now perform our first CRUD operation, create, specifically inserting a single document using the insert_1 method. This is where we see the Python dictionary truly shine as a MongoDB document. 1. Establishing the connection and collection. We start by recreating the client, database, and collection objects, targeting the customer's collection within our MongoDB_Python database. 2. Defining the document. Remember, a MongoDB document is just a Python dictionary. We will create a new customer record. Notice that we can easily include complex data types, like a list of favorite foods or nested address details, right in the same dictionary. We define our customer details in the dictionary name customer_document. 3. Executing insert_one. We call the insert_one method on our collection object and pass the dictionary. The operation returns an insert_one result object. MongoDB automatically generates a unique identifier, the _ID, for this new document, and we can access it from the result object. We print the insert_result inserted_ID to confirm the creation of the document. To summarize, you have successfully created your first MongoDB document from Python. Our next lecture 30.07, Insert Many. See you there. Welcome back. While insert_one is useful, applications often need to store many records efficiently. This is where the insert_many method comes in. It allows us to insert multiple documents with a single call to MongoDB. 1. Defining multiple documents. To use insert_many, we must provide a list of dictionaries. Notice the flexibility here. The first document has a phone field, but the second does not. MongoDB's flexible schema allows this without any issues. We define a list name, customer_list, containing 3 unique customer dictionaries. 2. Executing insert_many. We call the insert_many method on our collection object and pass the list of documents. The operation returns an insert_many result object, which is slightly different from the insert_one result. The insert_result.inserted_IDs attribute now holds a list of the unique _ID values generated by MongoDB for all 3 new documents. 3. The _ID field generation. If you do not explicitly include the _ID field in your Python dictionary, MongoDB automatically generates a unique object ID for each document, which is what happened here. If you choose to supply your own unique identifier, MongoDB will use it instead, provided it does not already exist. To summarize, we can now efficiently insert one or many documents into MongoDB. Our next lecture 30.08. Read. See you there. Welcome back. We have successfully created several documents. Now it is time for the most frequent database operation, reading data. In MongoDB, this is handled primarily by 2 methods, find_one and find. 1. Retrieving a single document with find_one. To fetch just one document that matches a specific criterion, we use find_one. The method accepts a Python dictionary as its first argument, which serves as the query filter. We want to find the customer whose name is Charlie. The find_one method returns a single matching Python dictionary or none if no match is found. Note that we do not use the cursor concept here, because it is only one item. 2. Retrieving multiple documents with find. To retrieve all documents that match a filter, we use the find method. This method returns a cursor object. To get the data, we must iterate over the cursor similar to PostgreSQL, or convert it to a list. The query dictionary is active:true. The find method gives us the cursor, _cursor, which we iterate over using a for loop to process each document. 3. Retrieving all documents. To get every document in the collection, simply call the find method without any arguments. This is the MongoDB equivalent of select star from table in SQL. We call collection.find parenthesis. To summarize, you can now insert and read data from MongoDB. Our next lecture 30.09. Update. See you there. Welcome back. We have covered create and read operations. Now we focus on update. The update operation in MongoDB requires a different approach from SQL, relying on update operators to safely modify fields without replacing the entire document. 1. The structure of an update operation. An update method, such as update_1, always takes at least two arguments. First, the query filter to select which document to update, and second, the update dictionary, which uses a special operator like $set. The $set operator is the most common, used to set the value of a specific field. Without an operator, MongoDB may try to replace the entire document. 2. Using update_1. Let us update Eve's city from Boston to New York and change her active status to false. We filter by name and use $set for the modification. Update_1 returns an update result object. We can check matched_count to see how many documents fit the query, and modified_count to see how many were actually changed. 3. Using update_many. If we want to update multiple documents that share a common attribute, we use update_many. Let us set all inactive customers to be in the city of Dallas. We only specify the query active:false. Update_many will apply the city change to all documents matching this filter. To summarize, you can now modify data in MongoDB. We have one operation left: delete. Our next lecture 30.10. Delete. See you there. Welcome back. We have reached the final CRUD operation for MongoDB. Delete. Just like with update, MongoDB provides methods to delete a single document or multiple documents based on a query filter. This is the simplest operation, but you must be careful with your filter. 1. Deleting a single document with delete_1. The delete_1 method requires only one argument: the query filter dictionary. We use this method when we know only one document should be removed. Let us delete the customer named Bob. The method returns a delete result object. The key attribute to check is deleted_count, which will be 1 if a document was successfully deleted. 2. Deleting multiple documents with delete_many. To remove all documents matching a specific condition, we use delete_many. Let us remove all customers whose active status is false. The deleted underscore count will now reflect the total number of documents that were removed by the operation, which may be greater than 1. 3. Caution: deleting all documents. If you pass an empty dictionary to delete_many, MongoDB will delete every single document in the collection. Always make sure your filter is correct to avoid massive data loss. To summarize, congratulations! You have successfully learned CRUD operations for both SQL and NoSQL databases. This wraps up our section on MongoDB. In the next section, we shift focus to a crucial development skill: debugging. Our next lecture 31.01. Use case. See you there. Welcome to Section 31, Debugging Fundamentals. As a developer, writing code is only half the battle. Fixing errors is the other half. In this section, we will learn how to find and fix bugs efficiently. 1. The scenario. Imagine we are building a simple shopping cart application. We have a list of products, each with a name and a price. Our goal is to calculate the total cost of all items in the cart. Take a look at this code. We initialize total_price to 0, loop through the products, and attempt to add each price to the total. 2. The unexpected result. Let's run the script. We expect the total to be 50 plus 100 plus 400, which equals 550. However, the output is 400. The script did not crash, and there are no syntax errors, but the result is clearly wrong. This is what we call a logical error. In a small script like this, you might spot the issue immediately, but in a large application, finding such bugs can be very difficult. To summarize, we have a buggy script that needs fixing. Instead of guessing, we should use a professional tool to inspect the code while it runs. Our next lecture 31.02, Debugging in VS Code. See you there. Welcome back. In the previous lecture, we discovered a logical error in our shopping cart script. The total was wrong, but we didn't know exactly why. Now, we will use the debugger in VS Code to pause the program and inspect it while it runs. 1. Setting a breakpoint. A breakpoint tells the computer to pause execution at a specific line. To set one in VS Code, hover your mouse over the gutter to the left of the line number and click the red dot. Let us place one inside our loop. 2. Starting the debugger. We select the Run and Debug tab and click on Run and Debug. The program will start, but it will freeze exactly at our breakpoint. This allows us to see the state of our application at that exact moment. 3. Stepping and inspecting. On the left side, look at the variables pane. We can see total underscore price is currently 0. Now use the step over button to execute this line. The variable updates to 50. Let's loop again. Step over. We are back at the line. Now watch closely. When we execute this line again, total underscore price becomes 100. It did not add 100 to 50. It simply replaced 50 with 100. We found the bug. We are using the assignment operator equals instead of plus equals. To summarize, by stepping through the code, we saw exactly where the logic failed. This is a fundamental skill for any developer. Next, we will move to a new syntax feature called match case. Join me in lecture 32.01, Introduction. See you there. Welcome to a new module focused on a powerful Python feature introduced in version 3.10, the match case statement. This is Python's answer to the switch or case statements found in other languages, providing a clean, structural way to handle multiple comparison conditions. 1. What is structural pattern matching? The match case statement isn't just a simple replacement for if-elif. It introduces structural pattern matching, which means it can compare an expression not just by its value, but also by its structure, allowing us to easily deconstruct data types like lists or objects. 2. Basic syntax and anatomy. The basic syntax starts with the match keyword, followed by the expression you want to test. Below it, you define one or more case blocks. Each case is a pattern. If the expression matches the pattern, the corresponding code block is executed. 3. The wildcard case. Notice the last case followed by an underscore. The underscore or wildcard pattern is similar to the else block in an if-elif-else chain. It acts as a catch-all, matching any value if all preceding cases fail. It should always be placed at the very end of your match block. 4. Variable capture. A powerful aspect is variable capture. If you use a single variable name in a case, not a literal value like start or 200, that variable name will match any value, and it will bind that value to the variable. This allows you to process the value within the case block. To summarize, this feature simplifies complex branching logic significantly. Our next lecture 32.02, Match Case versus If-Else. See you there. Welcome back. In the last lecture, we introduced the basic syntax of the match case statement. Today, we put it into context by directly comparing it with the long-standing Python method for multi-way branching, the if-elif-else structure. We will see how match case can simplify your code. 1. The traditional if/elif/else approach. For many years, this was the only way to handle multiple discrete comparisons in Python. As you can see, the structure requires repeated checks of the status variable, which can lead to verbose code and decreased readability when the logic becomes long. 2. The match case equivalent. Notice how much cleaner the logic is here. The expression to be checked, which is the status variable, is stated once at the top with match status. The code then clearly lists the possible cases. This clearly isolates the different logical paths, making the intent immediately obvious and the code easier to maintain. 3. Key takeaways. While if-elif-else can handle any condition, match case is specifically designed for structural pattern matching. It offers better readability for simple value-to-action mapping. In this basic example, match case is slightly cleaner and often more performant because it optimizes the branching process behind the scenes. However, remember that for complex conditional logic involving range checks or Boolean operations, if-elif-else might still be the appropriate tool. To summarize, use match case for clarity when mapping single inputs to specific outputs. Our next lecture 32.03, Syntax. See you there. Welcome back. While the basic match case syntax is straightforward, its power truly shines in more advanced use cases. In this lecture, we dive into two crucial syntactical features: matching multiple literal values in a single case and adding conditional guards using the if keyword. 1. Combining multiple literal values, or operator. Often, several distinct values should trigger the same action. Instead of writing multiple identical case blocks, you can use the vertical bar or operator to combine them. This pattern is concise and greatly improves readability, as shown here for grouping HTTP status codes by category. 2. Conditional guards, if keyword. When simple value matching is not enough, you can add a conditional guard using the if keyword immediately after a pattern. The guard expression must evaluate to true for the case block to execute. This is how you implement range checks, greater than or less than conditions within the match case structure. Notice we use a variable x to capture the value and check the condition against it. 3. Combining or and if guards. You can combine both features for complex yet readable logic. Here, the case matches if the status is either logged in or premium user, but only if the additional condition, that the user session active Boolean is true, is met. This demonstrates the expressiveness of the full match case syntax. To summarize, these features significantly extend the reach of match case beyond simple equality checks. Our next lecture 32.04, Using Collections. See you there. Welcome back. The true power of Python's match case is not just replacing simple if-elif statements, but its ability to perform structural pattern matching, especially when dealing with collections like lists and tuples. In this lecture, we will learn how to deconstruct or extract data directly from these structures. 1. Matching fixed-length tuples. the match case statement can match both the length and the content of a tuple. In this coordinate example, we check specific fixed values like 0 and use variable names like x and y to capture the corresponding values if the structure matches. This provides an elegant way to handle structured data. 2. Matching lists with wildcards. Match case works similarly with lists. Here, we match based on the length and the type of the elements inside. Case 2 matches any list of 3 elements where the first element is CMD, capturing the second and third elements into local variables for processing. This is a common pattern for processing command lists or data logs. 3. The splat operator asterisk for subsequences. For collections with variable length, we use the splat operator or asterisk similar to argument unpacking in Python functions. It captures all remaining elements into a list named details. This allows you to match the beginning and end of a sequence while collecting all the intermediate elements, making it ideal for parsing complex logs or headers. To summarize, structural pattern matching is a fundamental benefit of match case over traditional if-elif. Our next lecture 32.05, Using Constants. See you there. Welcome back for the final lecture on match case syntax. A frequent source of confusion is how the statement differentiates between a new variable that captures a value and a predefined constant that holds a specific value. We will clarify this distinction using Python's naming conventions and show you how to properly use constants in your patterns. 1. The ambiguity of variables in patterns. By default, any single lowercase name used as a case pattern is treated as a capture variable. This means it matches any input value and binds that value to the variable name. This behavior prevents subsequent cases from being reached, which is the source of the common name capture makes remaining patterns unreachable error. 2. The mandatory .access rule. To correctly match against a constant value, you must force Python to recognize it as a constant, not a capture variable. The safest and most common way is to define constants within a class or module and use the dot syntax to access them, like status.ok. This dot access signals to the match case engine that this is a constant value to be matched against, resolving the ambiguity and the syntax error. 3. Avoiding variable capture. As a final recap, always use the _wildcard case _ for your final, catch-all pattern, or whenever you want to match a value without capturing it into a named variable. Using any other lowercase name will create a capture variable, which is usually not what you intend for a catch-all case. To summarize, understanding this constant matching rule is essential for writing robust and bug-free match case statements. We now conclude our module on match case. Our next lecture is a brand new module, 33.01, Using Virtual Environment. See you there. Welcome to a new critical module focused on professional Python development practices, virtual environments. Up until now, we've relied on your system's main Python installation. This module will teach you why that approach is dangerous for real-world projects and how to isolate your dependencies safely. 1. Why virtual environments are essential. The core issue is dependency conflicts. Project A might require a library, say Pandas version 1.0, while Project B requires Pandas version 2.0. If both projects share the same system environment, installing the requirements for one project can break the other. A virtual environment solves this by creating an isolated, self-contained Python installation for each project. 2. Creating the environment. Python comes with a built-in module called venv. To create a virtual environment, you execute the command python 3-mven, followed by the name you choose for the environment folder. We call ours myproject.env. This command copies a minimal Python installation into that new folder. Three. Activating the environment. Creating it is only the first step. To start using the isolated environment, you must activate it. Activation means running a script inside the environments folder. The exact command depends on your operating system, but typically it involves sourcing the activate script. Once activated, your terminal prompt will change to show the environment's name. For deactivating. When you finish working on a project, you simply type the command deactivate. This exits the virtual environment and returns you to your main system's Python installation. To summarize, always use a virtual environment for every Python project to ensure clean, reproducible dependency management. Our next lecture is a new module, 34.01, Introduction to Unit Testing. See you there. Welcome to a crucial module on building reliable software. unit testing. Writing tests is the backbone of professional programming, ensuring that your code works as intended, remains functional as you make changes, and simplifies the debugging process. We will be focusing on Python's built-in unitest module. 1. What is a unit test? In programming, a unit is the smallest testable piece of code, usually a function or a method. A unit test is a written block of code that checks if a specific unit of your application is working correctly, isolated from the rest of the system. 2. Why do we write tests? The primary reason is verification and regression prevention. Verification means confirming your code meets its requirements. Regression prevention is critical. If you change one part of the code, a robust test suite immediately tells you if that change broke functionality elsewhere, saving countless hours of manual debugging. It is the safety net for refactoring. 3. The Python Unitest Framework. Python's standard library includes the Unitest framework, which is inspired by JUnit. All tests are organized into classes that inherit from unitest.testcase. Each test method within the class must begin with the word test underscore. Inside these methods, you use assertion methods like assert equal to verify that an expected result matches the actual result. To summarize, testing is essential. Now let's write our first test. Our next lecture 34.02, Create and Run a Test. See you there. Welcome back. In this lecture, we will move from theory to practice by creating a simple function and writing our first unit test for it. We will cover the correct file structure, the basic test assertion, and how to execute the test suite from your terminal. 1. The code under test. First, we need the code we want to test. We'll create a file named calculations.py with two simple functions, add and subtract. For this lecture, we will focus on writing tests for the add function. 2. Writing the test file. Following best practices, we create a separate file, typically named starting with test underscore, here test underscore calculations.py. We import unitest and the add function. Our test class inherits from unitest.testcase. We write two methods, both starting with test underscore, using the key assertion method self.assert equal to compare the actual output of our function with the expected output. 3. Running the test suite. The simplest way to run the tests is by executing the test file directly using Python, thanks to the if underscore underscore name underscore underscore equals equals underscore underscore main underscore underscore unitest.mange block. The output shows two dots, indicating two tests ran successfully, followed by a summary line confirming that the results are OK. To summarize, you can now write and execute basic unit tests. Next, we look at how to test for failures. Our next lecture 34.03, Assert for Exceptions. See you there. Welcome back. Good software doesn't just work when given valid input. It also handles invalid input gracefully by raising appropriate exceptions. In this lecture, we learn how to write tests that specifically verify our functions raise the expected exceptions using assert raises. 1. The code that raises an exception. Let's update our calculations.py file with a new divide function. This function explicitly checks for division by 0 and raises a 0 division error if the denominator b is 0. We must write a test to ensure this defensive coding works correctly. 2. Using self.assertRaises. We use the self.assertRaises method as a context manager with the with keyword. You pass the expected exception type, here 0 division error, as the argument. Any code executed inside this with block is expected to raise that specific exception. If it does, the test passes. If the code executes without raising the exception, or raises a different exception, the test fails. 3. Capturing the exception message, optional. For more rigorous testing, you can capture the raised exception object by assigning the context manager to a variable, here, context. You can then access the exception using context.exception and assert that the error message it contains matches your expectation. This ensures not only that the right error is raised, but also that the user receives the correct descriptive message. To summarize, testing for exceptions is crucial for validating the defensive capabilities of your code. Next, we look at managing test state. Our next lecture 34.04, Setup and Tear Down. See you there. Welcome back. In many testing scenarios, you need to perform the exact same setup steps, like creating a temporary file or initializing an object before every test. Similarly, you need to clean up those resources afterwards. In this lecture, we introduce the setup and teardown methods provided by the Unitist framework to manage this test lifecycle. 1. The need for setup and cleanup. Imagine you are testing a class that manages a database connection. You don't want to manually connect to the database in every test method, and you certainly don't want to leave open connections or temporary data cluttering your system. The setup and teardown methods are explicitly designed to handle this boilerplate setup and cleanup, ensuring each test runs in a clean, identical environment. 2. Implementing setup. The setup method is called automatically by the Unitist framework before every single test method in the class is executed. Here, we create an instance variable self.userdate, which is accessible by all the test methods. This ensures that every test starts with a fresh copy of the necessary initial data, preventing tests from affecting each other. 3. Implementing teardown. Conversely, the teardown method is called after every single test method, even if the test fails. It is used to release any resources acquired in setup. In a real-world scenario, this is where you would close database connections, delete temporary files, or reset global settings to ensure isolation and a clean system state. To summarize, setup and teardown guarantee test isolation and a reproducible environment. Our next lecture 34.05, Assignment. See you there. We have covered the core components of Python's Unitist framework, basic assertions, testing for exceptions, and managing resources with setup and teardown. Now it's time to apply these skills to a practical assignment. You will be testing a simple class designed to manage user tasks. 1. The Task Manager class. Your code under test is this simple Task Manager class. located in taskmanager.py. It has methods to initialize an empty task list, add a task, remove a task, and retrieve all tasks. Note that the remove task method raises a value error if the task does not exist. Your goal is to test all these functionalities. Two, assignment requirements. Create a file named test_taskmanager.py and write a test class. You must cover 4 specific requirements. First, use the setup method to initialize a new instance of the task manager class before every test. Second, write a test using self.assert to check if a task is added correctly and the length of the list is updated. Third, write a test using self.assert to confirm that removing a non-existent task raises a value error. Fourth, optionally, you can use teardown to check that the instance is properly cleaned up after tests. To summarize, start by setting up the instance in Setup, then create tests for successful addition and failed removal. Good luck! Our next lecture 34.06, Documentation. See you there. Welcome to the final lecture in our module on unit testing. We've learned how to write, run, and manage tests. The last critical step is documentation. Well-documented tests are just as important as documented production code, ensuring that other developers or your future self understand the test's intent and purpose. 1. Test method naming convention. The most basic form of test documentation is a clear, descriptive method name. The name should read like a sentence describing the exact scenario being tested, the input condition, and the expected outcome. Good naming eliminates ambiguity and allows anyone to instantly grasp the test's objective without reading the code inside the method. 2. Using docstrings for detailed context. For tests involving complex setups or subtle logic, adding a docstring is necessary. The docstring provides a concise summary of the test's specific goal, the preconditions, and any potential side effects. This documentation is crucial when debugging test failures, especially in large code bases. 3. Docstrings in test reports. Docstrings aren't just for reading the source code. Many advanced testing tools, like Nose2 or Pydantic, can optionally use the test docstrings to generate highly readable, human-friendly test reports, transforming cryptic test failures into clear, descriptive messages for the entire team. This capability underscores the value of writing good docstrings. To summarize, think of test documentation as code maintenance for your safety net. This concludes our module on unit testing. Our next lecture starts a new and exciting module, 35.01, Introduction to NumPy. See you there. Welcome to a major new module, NumPy, short for Numerical Python. If you plan to work in data science, machine learning, or scientific computing, NumPy is the foundational library you must master. It provides the essential tool for high-performance numerical operations, the n-dimensional array. 1. What is NumPy? NumPy is the fundamental package for scientific computing in Python. It centers around a powerful data structure called the ND array, which stands for n-dimensional array. This is a grid of values, all of the same type, indexed by a tuple of non-negative integers. It is the core data structure used by most other scientific Python libraries like Pandas and scikit-learn. Before importing NumPy, you must install it. You open your terminal and run this command. 2. NumPy array versus Python list. While Python lists can hold various data types, NumPy arrays are homogeneous. They hold only one data type. This uniformity is key to NumPy's speed. Lists store pointers to objects scattered in memory, requiring Python to dereference them one by one. NumPy arrays, however, store data contiguously and use optimized, precompiled C code for operations, resulting in orders of magnitude faster execution, especially for vectorization operations like multiplying every element by 2. Three. The import convention. The standard convention when importing NumPy is to alias it as npl. You will see this abbreviation used everywhere in the scientific Python ecosystem. Always follow this convention to make your code immediately understandable to other data professionals. To summarize, NumPy is essential for speed and efficiency in numerical work. Our next lecture 35.02, NumPy in action. See you there. Welcome back. Having learned why NumPy is crucial, it's time to start working with its core data structure, the ND array. In this lecture, we will cover the most common ways to create arrays, including initialization from Python lists, and using convenient methods to create arrays of zeros or ones. 1. Creating arrays from Python lists. The most common way to get started is by converting an existing Python list or a list of lists into an ND array using the np.array function. Note that a list of lists naturally creates a two-dimensional array, which is NumPy's way of representing a matrix. 2. Initialization methods. NumPy offers specialized functions for quick initialization. np.zeros and np.ones are used to create arrays filled with zeros or ones, respectively, which is useful for reserving space or initializing weights in models. The shape is always specified as a tuple. The np.arrange function works just like Python's range, but returns an ND array, making it ideal for creating sequences of numbers. 3. Element-wise operations. The key benefit of NumPy is vectorization. When you perform an arithmetic operation like addition or multiplication on two arrays, NumPy applies the operation element by element, or to all elements simultaneously in the case of multiplication by a scalar. This behavior is fundamentally different from Python lists, where the plus sign would concatenate the lists. Even comparison operators work element-wise, returning a Boolean array. To summarize, you now know the primary ways to create and perform basic operations on NumPy arrays. Our next lecture 35.03, linespace, logspace, and more. See you there. Welcome back. While np.arrange is useful for simple integer sequences, Scientific applications often require generating sequences with a specific number of points, spaced evenly or logarithmically. In this lecture, we explore the specialized NumPy functions, linspace, logspace, and random.rand for these advanced array creation tasks. 1. np.linspace. This function is essential for plotting and modeling. It takes a starting value, a stopping value, and the exact number of samples you want to generate. The samples are evenly or linearly spaced between the start and stop points, including both ends by default. You can exclude the stop value by setting the endpoint argument to false. 2. np.logspace. This function is used when you need points evenly distributed on a logarithmic scale, often for frequency analysis or financial modeling. Instead of specifying the start and stop values directly, you provide the exponents of the base, which defaults to 10. For example, logspace 0, 3, 4 generates 4 points from 10 to the power of 0 up to 10 to the power of 3. You can also change the base, for instance, to base 2. 3. Random array generation. The np.random submodule is essential for simulations and machine learning initialization. np.random.rand generates random floating point numbers in the range 0 to 1. np.random.randint generates random integers. Notice that for two-dimensional arrays, we specify the shape using the size argument and a tuple. To summarize, these functions give you fine-grained control over how you generate numerical data for analysis. Our next lecture 35.04, Using Math Functions. See you there. Welcome back. One of the biggest advantages of NumPy is its collection of universal functions, or ufuncs. These are vectorized wrappers around C functions that allow you to apply mathematical operations to every single element in an array without using explicit Python loops. This lecture will demonstrate how to use common ufuncs for trigonometry, logarithms, and exponentiation. 1. Standard mathematical operations. Many standard math functions are available directly through NumPy. The benefit is that when you call np.sqrt on an array, it calculates the square root of every element simultaneously and returns a new array with the results. This is significantly faster than writing a list comprehension in Python to do the same task. 2. Trigonometric and logarithmic ufuncs. NumPy provides a complete set of trigonometric functions like np.sine, np.cosine, and np.tan. Similarly, for logarithms, np.log calculates the natural logarithm, and np.log10 calculates the base 10 logarithm. All these functions operate element-wise. For example, to plot a sine wave, you can generate a linspace array and directly calculate its sine values with one line of code. 3. Aggregation functions. Beyond element-wise operations, NumPy provides powerful aggregation functions. Functions like np.sum and np.min calculate a single scalar result from the entire array. Most aggregation functions are also available as methods directly on the array object, such as ar.mean, which is often the more convenient syntax. To summarize, ufuncs are the foundation of NumPy's speed. Our next lecture 35.05, Array comparison. See you there. Welcome back. In Python programming, checking conditions is fundamental. In NumPy, when you use standard comparison operators, the operation is automatically vectorized, meaning the comparison happens element-wise. This lecture will show you how to leverage these element-wise comparisons to create powerful Boolean arrays, which are essential for filtering data. 1. Element-wise comparison operators. When you use operators like greater than, less than, or equal to on a NumPy array, it returns a new array of the exact same size, but filled with Boolean values, true or false. The first example compares every element to the scalar 35. The second example performs an element-by-element comparison between two arrays of the same shape, returning true only where the values match. Two. Boolean indexing or filtering. The power of these Boolean arrays is revealed when you use them as indices to select elements from the original array. This technique is called Boolean indexing or masking. NumPy returns only the elements from the original array where the corresponding value in the Boolean mask is true. This is an extremely common, fast, and idiomatic way to filter data in Python. 3. Combining comparison conditions. To combine multiple conditions, you must use the element-wise logical operators, the ampersand for and, the vertical bar for or, and the tilde for not. Critically, you must wrap each individual comparison in parentheses because of Python's operator precedence. This example filters for values that are greater than 20 and less than 50, extracting the elements 30 and 40. To summarize, Boolean indexing is a cornerstone of data analysis in NumPy. Next, we explore other comparison functions. Our next lecture 35.06. More comparison functions. See you there. Welcome back. In the previous lecture, we learned how to create Boolean masks using comparison operators. In this lecture, we will explore specialized NumPy functions that aggregate these Boolean results or provide conditional element selection, giving you more robust control over your data filtering. 1. Aggregate Boolean results. After creating a Boolean mask, you often need to summarize the result. The all function checks if every single element in the resulting Boolean array is true. The any function checks if at least one element is true. These methods are commonly chained directly onto the comparison operation itself. 2. Conditional selection. The np.where function is NumPy's vectorized equivalent of a ternary conditional operator or an if-else statement. It takes three arguments: a condition, the value to insert if the condition is true, and the value to insert if the condition is false. Here, we replace values greater than 25 with the string high, and the rest with low. If you only pass the condition, np.where returns the indices of the elements that meet the condition. 3. Floating point tolerance. Due to the inherent nature of floating point arithmetic, checking exact equality between floating point numbers often fails unexpectedly. The np.isClose function solves this. It checks if two arrays or values are equal within a specified tolerance, which is the standard practice for comparing floating point numbers in scientific computing. Always use np.isClose instead of the double equal sign when dealing with floats. To summarize, these specialized functions give you complete control over conditional logic in large arrays. Next, we will discuss an important topic: copying arrays. Our next lecture 35.07, Copying Arrays. See you there. Welcome back. When working with NumPy arrays, understanding how they are copied is crucial, as arrays behave differently from standard Python objects. This difference can lead to subtle bugs if you are not careful. This lecture will clarify the distinction between a view of an array, which shares data, and a copy, which is independent. 1. Views. A view is a new array object that refers to the data of the original array. This happens when you perform slicing, which we will cover in the next lecture, or when assigning arrays to a new variable without an explicit copy. If you modify the view, you modify the original array, and vice versa. This behavior is optimized for performance, as it avoids duplicating large amounts of data. In this example, changing array B also changes array A. 2. Creating a true copy. When you need a completely independent array, you must explicitly use the copy method. A true copy duplicates the array's data in memory, meaning any modifications made to the copy will not affect the original array, and vice versa. Use copy whenever you intend to modify the new array and must preserve the original. 3. The base attribute. You can programmatically check whether an array is a view or a true copy using the base attribute. If an array owns its data, like the original array or a true copy, base will be none. If it is a view, .base will refer back to the original array from which it was sliced or created. This is a handy debugging tool. To summarize, always be intentional about whether you need a view or a true copy. Our next lecture 35.08, Slicing. See you there. Welcome back. Slicing is a powerful and frequently used feature in NumPy, allowing you to select and modify subarrays. It works similarly to slicing Python lists, but with the crucial difference we discussed earlier. Slicing a NumPy array creates a view, not a copy. This lecture will cover standard slicing syntax for one-dimensional arrays. 1. Basic slicing syntax. Slicing uses the familiar Python list syntax: start: stop: step. The stop index is always exclusive. In the first example, we select indices 2, 3, and 4. Omitting the start index defaults to 0, and omitting the stop index defaults to the end of the array. 2. Using the step argument. The third argument in the slicing notation determines the step size. Using a step of 2 selects every other element. A common trick is using a step of -1, ::1, which efficiently reverses the entire array. 3. Slicing creates a view. As a final note, remember the critical distinction. Slicing generates a view. If you assign new values to the slice portion, the corresponding elements in the original array are modified because they share the same memory. If you need an independent copy, you must explicitly chain the copy method after the slice, like array start: stop. Copy. To summarize, slicing is efficient but requires caution regarding data sharing. Our next lecture 35.09, Multidimensional Arrays. See you there. Welcome back. While one-dimensional arrays are useful, the true power of NumPy lies in its ability to efficiently handle multidimensional arrays, most commonly two-dimensional arrays, or matrices. This lecture will show you how to index and slice these higher-dimensional structures. 1. Creating 2D arrays. A 2D array is typically created from a list of lists, where each inner list represents a row. We call this structure a matrix. The order of dimensions is important. Rows come first, then columns. The .ndim attribute confirms the number of dimensions, which is 2 for a matrix. 2. Indexing 2D arrays. To access a single element, you use a single pair of square brackets, containing the row index and the column index, separated by a comma. This is the preferred way. Matrix square bracket row index comma column index square bracket. If you only provide the first index, NumPy returns the entire corresponding row. 3. Slicing 2D arrays. Slicing works by applying slicing notation to both the row and column dimensions, separated by a comma. The colon alone acts as a wildcard, selecting everything in that dimension. In the first example, we select rows up to index 2 and all columns. In the second, we select all rows and only the column at index 1. Remember, all these slicing operations also create views, sharing memory with the original matrix. To summarize, mastering comma-separated indexing and slicing is vital for manipulating matrices in data science. Our next lecture 35.10. Few more attributes. See you there. Welcome back. To work effectively with NumPy arrays, you need to be able to quickly inspect their key characteristics. NumPy arrays provide several attributes, properties of the object, that tell you about their dimensions, data type, and total size. In this lecture, we will cover the most frequently used attributes. 1. The .shape attribute. The .shape attribute returns a tuple of integers indicating the size of the array in each dimension. This is perhaps the most important attribute. For a 1D array, it returns a single number followed by a comma. For a 2D array, it returns the number of rows followed by the number of columns. Understanding the shape is vital before performing operations like matrix multiplication. 2. The .type attribute. Since NumPy arrays are homogeneous, the .dtype attribute tells you the data type of the elements stored in the array. This is often int64, 4 integers, or float64, 4 floating point numbers. NumPy uses fixed-size types for efficiency. Checking the dtype is crucial, as the type affects how operations are performed and how much memory the array consumes. 3. The size and ndim attributes. The size attribute returns the total number of elements in the array, the product of the numbers in the shape tuple. The ndim attribute, which we saw earlier, explicitly returns the number of dimensions, which is equivalent to the length of the shape tuple. For our 2x5 array, The size is 10 and the number of dimensions is 2. To summarize, these attributes provide the essential metadata for your NumPy arrays. Next, we will cover some final useful functions before moving on. Our next lecture 35.11. Few more functions. See you there. Congratulations on reaching the final lecture of our NumPy module. We'll conclude by covering 3 essential utility functions: sorting array elements, reshaping an array into a new structure, and flattening a multidimensional array back into one dimension. These functions are frequently used in data preparation pipelines. 1. Sorting arrays. The np.sort function returns a sorted version of the input array. It is important to note that, unlike Python's list.sort method, np.sort does not modify the original array in place. It returns a new sorted copy. This behavior helps maintain data integrity during complex analysis. 2. Reshaping arrays. The reshape method changes the shape of an array without changing its data. It is crucial for preparing data for machine learning models, which often require specific input shapes. The total number of elements must remain the same, 12 in this case. You can use -1 as one of the dimensions. NumPy will automatically calculate the size of that dimension based on the total number of elements. Reshaping creates a view, sharing data with the original array. 3. Flattening arrays. The Revel method is used to flatten a multidimensional array into a one-dimensional array. This is often necessary before feeding data into a linear model. Like reshape, Revel generally returns a view of the original array for efficiency. If you need a guaranteed independent copy, use the similar method flat, which explicitly forces a copy to be made. To summarize, these functions complete your toolkit for manipulating numerical data efficiently. We are now ready to move on to the powerful data structure library, Pandas. Our next module begins with lecture 36.01, Introduction to Pandas. See you there. Welcome to a crucial new module on Pandas. If NumPy is the foundation of scientific computing in Python, Pandas is the universal tool for data manipulation and analysis. It provides high-performance, easy-to-use data structures and data analysis tools, making it the industry standard for handling tabular data. 1. What is Pandas? Pandas is an open-source Python library providing high-performance, easy-to-use data structures and data analysis tools. It is built on top of the NumPy package, meaning that NumPy's fast array operations are integrated into Pandas. Pandas is ideal for working with relational or labeled data, similar to data found in spreadsheet programs or SQL tables. Before importing, we must install Pandas. You open your terminal and run this command. 2. The import convention. Just like NumPy, Pandas has a standard import convention. you should always import it as import pandas as PD. This convention is universally used and ensures your code is recognizable and consistent within the Python data community. 3. Core data structures. Pandas introduces two primary data structures. First is the series. Think of a series as a single column of data, similar to a 1D NumPy array, but with labels called an index. Second is the data frame. This is the most common structure, representing data in rows and columns, like a table or spreadsheet. A data frame is essentially a collection of series objects that share the same index. We will focus heavily on both of these in the coming lectures. To summarize, Pandas is the key to working with real-world data. Our next lecture 36.02 series. See you there. Welcome back. In the last lecture, we introduced the series and the data frame. Today, we focus entirely on the series. Understanding the series is the foundational step because a data frame is, at its core, a collection of series objects aligned along a shared index. The series is the one-dimensional workhorse of Pandas. 1. Definition of a series. A Pandas series is a one-dimensional array-like object capable of holding any data type, such as integers, strings, floating point numbers, or Python objects. It consists of two main parts: the data, which is essentially a NumPy array, and the associated index, which labels each element. 2. Data versus index. When we create a series from a standard Python list, Pandas automatically assigns a default numeric index starting from 0, just like a list index. In the output, the right-hand column shows the actual data values, and the left-hand column shows the index labels, which are 0, 1, 2, and 3. The data type, or D type, is shown at the bottom. 3. Series attributes. You can access the two main components using attributes. The values attribute extracts the data as a pure NumPy array, stripping away the index. The index attribute returns the index object itself. This is particularly useful for verifying the labels. Finally, the D-type attribute tells you the Pandas data type, mirroring the NumPy D type. To summarize, the index is what separates a series from a simple NumPy array. Our next lecture 36.03, Create Project. See you there. Welcome back. Before we dive into creating and manipulating Pandas series objects, let's take a quick moment to set up our project files. Having a clean and organized structure will make it easy to follow the coding examples throughout this module. 1. Creating the demo files. We will create two main files for this module. The first is series_demo.py. This file will contain all our examples and code related to the one-dimensional series data structure. The second is dataframe_demo.py. We will use this file for all our examples involving the two-dimensional data frame structure. 2. Initial imports. In both of these files, add the standard import lines. We need import pandas as PD, and since pandas relies heavily on NumPy, we also include import numpy as NP. This ensures all the necessary libraries are ready to go when we start coding. To summarize, your environment is set up. Our next lecture 36.04. Create and use series. See you there. Welcome back. In this lecture, we will get hands-on with the Pandas series object. We'll demonstrate how to create a series from various standard Python structures and explore how to access individual elements using the default integer index. 1. Creating series from Python objects. There is a way to create a series is by passing a data structure into the pd.series constructor. When passed a Python list or a NumPy array, Pandas uses the data and automatically assigns a default numeric index, starting at 0. Notice how the d-type is inferred from the input data. 2. Series from a scalar value. You can also create a series from a single scalar value. However, you must explicitly provide an index to tell Pandas how many times to repeat that value. Here, we pass the scalar 5 and an index list of length 5, resulting in a series where all 5 values are equal to 5. 3. Accessing elements by index. You access elements in a series using the square bracket notation, similar to accessing items in a list. When using the default index, you pass the numeric position. For the series with values 10, 20, 30, passing 0 returns 10, and passing 2 returns 30. To summarize, creating a series is straightforward. Next, we will explore the real benefit of the series, using custom, meaningful index labels. Our next lecture 36.05. Use custom indices. See you there. Welcome back. The true power of a Pandas series, beyond a simple NumPy array, is its ability to use meaningful, custom index labels. In this lecture, we will learn how to assign non-numeric labels to our data, making data retrieval much more intuitive. 1. Creating series with custom indices. To assign custom labels, you pass a list of labels to the index argument in the pd.series constructor. These labels can be strings, dates, or other meaningful identifiers. This allows us to retrieve data using a label that directly describes the information, like a dictionary key. 2. Accessing elements by label index. Once custom indices are set, you can retrieve elements by passing the label string directly in the square brackets. This is much more robust than relying on integer positions, as the data remains labeled even after sorting or restructuring. You can also retrieve multiple items by passing a list of labels. 3. Accessing elements by position index. Even with custom labels, the series retains its underlying zero-based integer positioning. You can still access elements using the numerical index, and this method is necessary for slicing by position. However, it is generally better practice to use the label index for accessing specific labeled data points. To summarize, custom indices turn numerical arrays into self-describing data objects. Our next lecture 36.06. Series of strings. See you there. Welcome back. While we've primarily worked with numerical data so far, Pandas truly shines when working with real-world, often messy, string data. This lecture explores how to create and, more importantly, efficiently manipulate series composed of strings using Pandas' vectorized string methods. 1. Creating a series of strings. Just like numbers, you create a series of strings by passing a list of string values. The D-type is typically object or string, depending on your Pandas version. Notice that in real-world data, strings often contain unwanted leading or trailing whitespace or inconsistent capitalization. This is where vectorized methods become essential. 2. Vectorized string methods. Python string methods like lower or strip normally operate only on a single string. Pandas introduces the str accessor, which allows you to apply these methods to every single string element in the series, without writing an explicit loop. Here we use .str.strip to remove whitespace, and then chain.str.lower to standardize the capitalization. This element-wise application is fast and clean. 3. Conditional string operations. You can also perform checks on the strings. For example, .str. contains checks if a substring is present in each element and returns a Boolean mask. We can then use this mask, which we learned about in the NumPy module, to filter the original series and extract only the cities containing the letter O. To summarize, the .str accessor is your key tool for text processing in Pandas. Our next lecture 36.07. Describe. See you there. Welcome back. A crucial first step in any data analysis project is getting a quick overview of your data's statistical properties. Pandas provides a powerful single method for this, the .describe method. This lecture will show you how to use .describe to generate descriptive statistics for numerical data in a series, and what happens when you use it on string data. 1. .describe on numerical data. When applied to a series containing numerical data, the .describe method returns a new series containing 8 key statistical measures. These include the count of non-null values, the mean, the standard deviation, the minimum and maximum values, and the quartile values, the 25th, 50th, and 75th percentiles. This provides an excellent snapshot of the data's distribution and potential outliers. 2. .describe on object or string data. When applied to non-numerical data like strings, .describe returns a different set of summary statistics relevant to categorical data. These typically include the count, the unique count, the top or most frequent value, and its frequency. This is useful for understanding the diversity and distribution of categories within your dataset. 3. Calculating individual statistics. While .describe is great for a quick overview, you can also access any of the individual statistics directly using dedicated methods on the series object, such as .mean, .median, .max, and .min. These methods return a single scalar value. To summarize, .describe is your go-to function for initial data profiling. Now that we understand the series, we are going to move on to the primary data structure of Pandas, the data frame. Our next lecture 36.08. Data frame. See you there. Welcome back. We are now moving on to the most important structure in Pandas, the data frame. This is the primary data structure used for all tabular data, representing data in rows and columns, just like a spreadsheet or a SQL table. Understanding its components is key to mastering data analysis in Python. One, definition of a data frame. A Pandas data frame is a two-dimensional, size-mutable, and potentially heterogeneous tabular data structure. Think of it as a dictionary of series objects, where the keys are the column names. Each column is a series, and all series share the same index, ensuring that the data across rows is aligned. Two indices, rows and columns. Unlike a series which has one index, a data frame has two. The row index, often just called the index, labels each record or observation, similar to the series index. The column index, or column labels, names each variable or feature, usually referred to simply as the columns. You can access these labels directly. Three, data frame structural attributes. Like NumPy arrays and series, data frames have useful attributes. The shape attribute returns a tuple of rows, columns. The ndim attribute is always 2 for a data frame. Unlike the series, the dtypes attribute returns a series listing the data type for each column, reflecting the data frame's heterogeneous nature. To summarize, the data frame is the cornerstone of data manipulation in Python. Our next lecture 36.09, Create Data Frame. See you there. Welcome back. In the last lecture, we learned that a data frame is a table with labeled rows and columns. In this lecture, we'll cover the most common way to construct a data frame, using a Python dictionary where keys become column names and values become the data within those columns. 1. Creating data frame from a dictionary of lists. This is the simplest and most intuitive method. You organize your data into a Python dictionary where each key is a column name, and the corresponding value is a list of data for that column. When passed to the pd.dataframe constructor, Pandas creates columns from the keys and assigns a default numeric index to the rows. Two, specifying column order. By default, Pandas often maintains the insertion order of the dictionary keys, but for guaranteed consistency, or to reorder the columns, you can pass an explicit list of column names to the columns argument. 3. Assigning custom row indices. Just like with the series, you can assign custom labels to the rows by using the index argument. Here, we use a 1, 2, 3 index instead of the default 0, 1, 2, which can be useful for human-readable indexing. To summarize, data frames are highly flexible upon creation. Our next lecture 36.10, Access columns and rows. See you there. Welcome back. Having created a data frame, the next critical step is learning how to efficiently retrieve specific data. In this lecture, we cover the primary methods for accessing columns, which are returned as series objects, and accessing rows, which requires the use of special accessors. 1. Accessing columns using bracket notation. Accessing columns is similar to accessing values in a Python dictionary. You pass the column name as a string inside square brackets. The result of extracting a single column is always a Pandas series. You can verify this by checking the type. 2. Accessing columns using dot notation. As a shortcut, you can often use dot notation, like df.tem, provided the column name contains no spaces or special characters and doesn't conflict with built-in data frame methods. While convenient, the bracket notation is generally safer and more flexible. 3. Accessing rows by label. To access rows, you must use one of the specialized row accessors. The first is .lock, which stands for location. It is strictly label-based. You pass the custom row label inside the square brackets after .lock. The result is a Pandas series, where the original column names become the new series index labels. 4. Accessing rows by position. The second accessor is .ilock, which stands for integer location. It is strictly position-based, meaning you use the zero-based integer index, regardless of whether the row has custom labels. This is necessary if you need to access a row based on its physical order in the data frame. To summarize, always use .lock or .ilock for rows and square brackets for columns. Our next lecture 36.11. Use slicing and lists. See you there. Welcome back. In the previous lecture, we accessed single columns and rows. Now, we expand those concepts to retrieve subsets of our data, multiple columns and multiple rows at once. Mastering slicing and using lists within the accessors is essential for extracting specific data blocks. 1. Selecting multiple columns. To select more than one column, you pass a list of column names inside the square brackets. Note that this requires double brackets. The outer brackets are for indexing, and the inner brackets define the list of column names. Crucially, selecting multiple columns returns a new data frame, not a series. 2. Slicing rows with .lock. When slicing rows using .lock and custom labels, the stop label is inclusive. This means the row with label R3 is included in the result, unlike standard Python slicing. We specify the start row and the end row, separated by a colon. 3. Slicing rows with .ilock. When slicing with .ilock, we use the zero-based integer positions, and the stop index is exclusive, behaving exactly like standard Python list slicing. Here, 1:3 selects rows at position 1 and position 2. To summarize, mastering the inclusive nature of .lock slicing and the exclusive nature of .ilock slicing is crucial. Our next lecture 36.12. Getting a subset. See you there. Welcome back. We have learned how to select columns and how to select rows. In real-world analysis, you often need to select a specific rectangular subset of your data, a block of several rows and several columns. This is achieved by combining the row and column selection methods using the .lock or .ilock accessors. 1. Setup. Custom Index Data Frame. We first create a small 3 by 4 data frame with custom labels for both rows, R1, R2, R3, and columns, C1 through C4. This allows us to clearly demonstrate the label-based and position-based access. 2. Selecting subsets with .lock. To select a rectangular subset, we use the syntax df.lock, row selector, column selector. The row and column selectors are separated by a comma. We can use slicing for the rows, say R2 to R3, and a list for the columns C1 and C3. Remember, .lock slicing is inclusive, so R3 is included. 3. Selecting subsets with .ilock. Similarly, .ilock uses integer positions. We can use a list for the rows 0 and 2 and slicing for the columns 1:4. Remember, .ilock slicing is exclusive, so position 4 is not included. This syntax is extremely powerful for extracting any part of your data table. To summarize, the combination of row and column selectors allows precise subsetting. Our next lecture 36.13, Query for Data. See you there. Welcome back. While structural indexing like .lock is useful, the true power of data analysis lies in conditional selection. Asking your data questions like, show me all records where the value is greater than a certain threshold. This is achieved using Boolean masking, which relies on the concepts we learned in the NumPy module. 1. Creating the data and a single condition. To filter data, we first create a Boolean series or mask. We access the price column and apply a condition, asking if the price is greater than 200. The result is a series of true and false values, corresponding row by row to whether the condition was met. This mask is the key to conditional selection. 2. Filtering the data frame. To filter the data frame, you pass the Boolean mask directly inside the square brackets of the data frame. Pandas automatically selects only the rows where the mask is true. This operation extracts all columns but only the rows that satisfy the condition. 3. Combining multiple conditions. For complex queries, you can combine multiple conditions using the bitwise operators. Use the ampersand sign, for and the pipe sign, for or. It is essential to wrap each individual condition in parentheses to ensure correct operator precedence. To summarize, Boolean masking is the primary way to perform database-style queries on your data frame. Our next lecture 36.14, Pick a Cell. See you there. Welcome back. We've covered how to access entire columns, rows, and rectangular subsets. The final and arguably most precise access method is picking out or modifying a single individual cell value within the data frame. For this, Pandas provides two highly optimized accessors, .at and .iat. 1. Setup, sample data frame. We will work with a simple data frame that has custom row indices R1, R2, R3, and column names A and B. 2. Accessing a single cell by label using .at. The .at accessor is designed for label-based lookup of a single value. Its syntax is df.at, row label, column label. This method is significantly faster than using .lock for single-value lookups. You can also use .at to assign a new value to the cell, as we do here by changing the value at R2, B to 999. Three. Accessing a single cell by position using .iat. Similarly, the .iat accessor is optimized for integer-based, positional lookups. Its syntax is df.iat, row position, column position. This is the fastest way to access a single cell by its physical coordinates. We can also use it to set a new value, like changing the cell at position 1, 0 to 888. To summarize, .at and .iat are your preferred methods for working with individual cell values. Our next lecture 36.15, Describing and Transposing. See you there. Welcome back. In this lecture, we look at two utility functions that are incredibly useful for initial data exploration. First, reapplying the .describe method to the data frame, and second, transposing the data frame to quickly swap rows and columns. 1. .describe on a data frame. When you apply .describe to a data frame, it automatically computes the descriptive statistics only for the numerical columns, treating each numerical column as an independent series. The resulting data frame provides a clean table of statistics, making it easy to compare the central tendency and spread across different variables. Two. Transposing the data frame. Transposition is a mathematical operation where rows become columns and columns become rows. In Pandas, this is done by simply accessing the .t attribute. This is useful when you have many columns and few rows, and you want the data to be more readable. For example, if you describe a data frame and the result is too wide, transposing it can make the statistics much easier to view vertically. 3. Analyzing transposed statistics. Combining these two concepts is a common technique. By calling df.describe.t, we first calculate the statistics and then transpose the resulting table. This is often the preferred way to view descriptive statistics, as it lists the column names vertically and the statistics horizontally. To summarize, .describe and transposition are great tools for initial data inspection. Our next lecture 36.16, Sorting. See you there. Welcome back. Sorting data is a fundamental step in almost any analysis, whether you want to quickly find the top performers or organize time series data chronologically. In Pandas, we have two primary methods for sorting, one for sorting by the values within columns, and one for sorting by the index labels. 1. Setup, sample data frame. We start with a data frame containing city data, with columns for city name, population in millions, and an existing rank. Notice the current row order is arbitrary, not sorted by any meaningful column. Two, sorting by column values. The df.sortValues method is a way to sort. You must pass the column name to the by argument. To change from the default ascending order to descending, you set ascending to false. Notice that the entire row moves when sorted, but the original index values 0 through 3 are retained next to the correct data. Three, sorting by multiple columns. You can specify multiple sort columns by passing a list to the by argument. Pandas sorts by the first column, and then uses the second column as a tiebreaker, and so on. 4. Sorting by index labels. If you want to sort the rows based on the row labels rather than column values, you use the df.sortIndex method. This method has no by argument. You can still control the order using the ascending argument, which defaults to true. To summarize, sorting is essential for data organization. Our next lecture 36.17, Working with CSV Files. See you there. Welcome to the final segment of our Pandas module, where we shift our focus from creating data frames manually to working with real-world data files. There is a format for sharing tabular data is the comma-separated values, or CSV, file. Understanding how to interact with CSV files is a requirement for any data scientist. 1. What is a CSV file? A CSV file is a plain text file that stores tabular data. Each line in the file represents a data record, and each field, or column value, in the record is separated by a comma or another delimiter. This format is simple, universally compatible with most data tools, and highly efficient for storing large datasets. 2. Pandas and File I/O. Pandas is the bridge between your text-based CSV files and the powerful data frame object. It provides highly optimized functions for reading data from external files into a data frame and for writing a data frame back out to an external file. 3. The core CSV functions. We will focus on two main functions. To bring data in, we use pd.read_CSV. This function reads the data and returns a data frame object. To export data, we use the dataframe method .to_CSV. This method writes the data frame content to a specified file path. To summarize, CSV files are crucial for data exchange. Our next lecture 36.18, Read Data. See you there. Welcome back. In this lecture, we focus on the function for importing data, reading a CSV file into a data frame using the powerful pd.read_CSV function. We will cover the basic usage and two essential arguments for correctly structuring your data upon import. 1. Basic CSV data import. The simplest usage of pd.read_CSV only requires passing the file path. By default, Pandas is optimized for standard CSV files, meaning it assumes commas separate the values, and the first line contains the column headers. The result is always a data frame, and we use the .head method to quickly inspect the first 5 rows. Two, handling non-standard CSV delimiters. Although we call them CSV files, they don't always use a comma. If your file uses a different character, like a semicolon or a pipe, to separate the values, you must specify it using the sep argument. Failing to do so will result in a data frame with only one column containing all the data lumped together. Three, specifying the index column. If your data file contains a column that serves as a unique identifier and should be used as the custom row index for cleaner access, you use the index_call argument. You can pass either the column's name, such as ID, or its zero-based position. This moves the chosen column from the data area to the row label area. To summarize, .read_CSV is essential for getting data into Pandas. Our next lecture 36.19, Write Data. See you there. Welcome to the final lecture in our Pandas module. After all the analysis and data manipulation, the last crucial step is saving your work. In this lecture, we cover how to use the data frame method, .to_CSV, to export your clean, processed data frame back into a CSV file, and how to prevent unwanted elements from being written. 1. Basic data export. To save your data frame, you simply call the .to_CSV method on the data frame object and pass the desired file name as an argument. By default, this method includes the column headers on the first line and, importantly, writes the row index as an extra, unlabeled column. Two, omitting the row index. Since the automatically generated row index is often unnecessary for the recipient, it is common practice to omit it. You do this by setting the index argument to false. 3. Omitting column headers. In some specific cases, like appending data to an existing file, you may not want to include the column names. To suppress the column names, you set the header argument to false. Here we also combine it with index equals false to produce a file containing only the raw data. To summarize, the .to_CSV method is essential for exporting your final data product. This concludes our section on the Pandas library. You now have the skills to create, manipulate, and analyze tabular data. Our next section is Matplotlib, starting with lecture 37.01, Introduction. See you there. Welcome to the next major section of our course, Data Visualization. We have learned how to collect, clean, and analyze data using NumPy and Pandas. Now, we must learn how to communicate our findings visually. Maybe the most fundamental and widely used plotting library in Python is Matplotlib. 1. What is Matplotlib? Matplotlib is a comprehensive library for creating static, animated, and interactive visualizations in Python. It is designed to be highly customizable, allowing you to create publication-quality figures, charts, and plots. Think of it as the original core drawing tool for Python data science. 2. Why visualize data? While statistics like the mean and standard deviation are useful, they can often hide critical information. Visualization helps us identify trends, patterns, and outliers that are invisible in raw data tables. A well-designed plot can communicate complex information almost instantly. Before importing, you must install first. You open your terminal and run this command. 3. The PyPlot module. Matplotlib is a very large library, but almost all introductory plotting is done through the pyplot submodule. This module provides a simple interface that is modeled after MATLAB, making it straightforward to generate figures and axes. Standard practice is to import it using the alias plt. 4. The plotting workflow. The basic workflow is simple. First, prepare your data, typically using NumPy or Pandas structures. Second, use a plt function, such as plt.plot, to define the visual elements. And third, use plt.show to render and display the final figure. To summarize, Matplotlib and pyplot are our tools for visualization. Our next lecture 37.02, Create Project. See you there. Welcome back. Before we can draw our first chart, we need to set up our project environment. Since Matplotlib relies heavily on numerical data, we will import both Matplotlib's pyplot module and NumPy to efficiently create and manage the data we are going to visualize. 1. Project setup and file creation. Start by creating a new folder named matplotlib_projects to house all our visualization work. Inside this folder, create a new Python file named charts.py. We will write all our code in this file for the next few lectures. 2. The essential imports. The two import statements shown are the foundation of nearly every Matplotlib project. We import matplotlib.pyplot and commonly give it the alias plt. We also import NumPy as np, as its array generation capabilities, like np.arrange and np.linspace, are ideal for quickly creating sample data for plotting. 3. Writing the project boilerplate. For simplicity, we establish a basic code structure right away. We define simple x and y data using NumPy, followed by placeholders for the plotting and showing functions. This three-step structure, data, plot, show, will be repeated in every plot we create. To summarize, set up your file with the necessary imports and the basic three-step structure. Our next lecture 37.03, Generate Line Plot. See you there. Welcome back. In this lecture, we generate our first actual chart, the line plot. Line plots are the standard for visualizing time series or trends where data points are connected in sequence. We will use the main plotting function in the pyplot module, plt.plot. 1. Preparing x and y data. For a line plot, you need two sequences of the same length, X values for the horizontal axis and Y values for the vertical axis. We use NumPy's linspace to generate 50 evenly spaced points between 0 and 10 for X, and then calculate the sign of those X values for Y. It is crucial that both arrays have exactly the same length and correspond element by element. Two, generating the plot. The core plotting function is simple. plt.plot. You pass the X array first, followed by the Y array. This function internally creates the figure and draws the line by connecting the corresponding X, Y points. However, calling this function does not immediately display the output. 3. Displaying the plot. To actually render and display the generated chart, you must call plt.show. This function executes the plotting commands, opens a separate window showing the figure, and stops the execution of the code until the window is closed. Always remember to call plt.show at the end of your plotting script. To summarize, the three-step process data, plot, show is the foundation. Our next lecture 37.04. Add color and grid. See you there. Welcome back. While the basic line plot works, it often lacks visual context. In this lecture, we learn how to significantly enhance readability by customizing the line color and style, adding markers to highlight data points, and including a grid to help estimate values along the axis. 1. Setup. Basic line plot data. We begin with a simple parabola function. This straightforward dataset will help us clearly see the effect of various styling arguments we apply to the line plot. 2. Customizing line color and style. You can control the appearance of the line using keyword arguments within plt.plot. Use color to set the line color, using either English names like green or hexadecimal codes. Use line style to set the line pattern, such as a dashed line represented by 2 dashes. Finally, used marker to place symbols at each data point, such as O for a circle. 3. Adding a grid. To make it easier for viewers to estimate the values of points, we can add a grid to the background of the plot using plt.grid and setting its argument to true. This adds horizontal and vertical reference lines extending from the tick marks on the axis. This should be called before plt.show. 4. Displaying the enhanced plot. Running the code now displays the plot with all our customizations, the green, dashed line, circle markers, and the background grid. You can see how much more informative the plot becomes with these simple additions. To summarize, these simple style elements greatly improve plot clarity. Our next lecture 37.05. Control transparency. See you there. Welcome back. When plotting multiple datasets, especially when lines or markers overlap, it can be difficult to distinguish individual elements or see where data points are densely clustered. In this lecture, we introduce the alpha parameter, which controls the transparency of any visual element, a simple yet powerful tool for handling overlapping plots. 1. Defining overlapping data. To properly demonstrate transparency, we need data sets that overlap. We use NumPy to create 3 different y series: sine, cosine, and tangent, all based on the same x data. These 3 lines will naturally intersect multiple times. Two, using alpha for transparency. The alpha parameter takes a floating point value between 0 and 1, where 1 is the default, fully opaque setting. We plot the 3 lines with progressively lower alpha values. Notice how the blue line with the default alpha of 1 completely obscures anything underneath it. The red and especially the green lines with lower alpha values allow us to see the other lines where they overlap. Three, adding a legend. Since we used the label argument in our plot calls, we can easily generate a legend using plt.legend. The legend shows the color and style of each line and its corresponding label, which is essential for identifying which transparent line is which. Running this code now shows the final visualization. To summarize, the alpha argument is key for clarifying plots with high data density or many overlapping series. Our next lecture 37.06, Generate Scatter Graph. See you there. Welcome back. While line plots show trends over a continuous range, scatter plots are ideal for visualizing the relationship, correlation, and distribution between 2 different variables. In this lecture, we switch from plt.plot to the dedicated function for point data, plt.scatter. 1. Preparing data for scatter plot. We generate 50 random data points for x and y. Crucially, the scatter plot is powerful because it allows the size and color of each individual point to be controlled by 2 additional independent variables. We create colors and size arrays for this purpose. Two, generating the basic scatter plot. The syntax for plt.scatter is similar to plt.plot. X data first, then Y data. Unlike the line plot, the scatter function draws unconnected markers at each X, Y coordinate. 3. Controlling point size and color. To use our auxiliary variables, we pass the size array to the S argument, making each marker proportional to its corresponding size value. We pass the colors array to the Cth argument, allowing the color of each point to map to its color value according to a defined color map, such as Voridus. We also add transparency using alpha to better visualize overlapping data points. This creates a powerful 4-dimensional visualization: X, Y, size, and color. To summarize, scatter plots are excellent for exploring multidimensional data visually. Our next lecture 37.07, bar graph. See you there. Welcome back. Bar graphs are the gold standard for visually comparing the magnitudes of discrete categories. Unlike line or scatter plots, bar graphs plot categorical variables on the x-axis and their numerical values or frequency on the y-axis. We will use the plt.bar function to generate these plots. 1. Preparing categorical data. To plot categories, we need two things: the category names or labels for the x-axis and the numerical values for the height of the bars. Matplotlib's plt.bar requires numerical positions for the bars, so we use NumPy's arrange to create a simple sequence x_pos that corresponds to the number of categories. 2. Generating the bar plot. We call plt.bar, passing the numerical positions x_pos and the values. We use the width argument to control how much space each bar occupies. A value of 0.8 is standard. We also specify the color. At this point, the x-axis still shows the numerical positions 0, 1, 2, 3, not the category labels. 3. Labeling the x-axis. To display the actual category names, we use the plt.xticks function. This function takes two arguments. First, the positions where the ticks should appear, which is x_pos, and second, the corresponding categories, text to be placed at those positions. We then add a title and y-axis label before showing the final, correctly labeled graph. To summarize, bar graphs require careful handling of numerical positions and categorical labels. Our next lecture 37.08, Histogram. See you there. Welcome back. While bar charts compare categories, the histogram is specifically designed to show the distribution of a single, continuous numerical variable. It allows us to see how frequently different values or ranges of values occur in our dataset. We use the dedicated function plt.hist for this visualization. 1. Preparing continuous data. Unlike previous plots that needed both x and y arrays, a histogram requires only one continuous array of values. We generate 1,000 random data points that follow a standard normal distribution, meaning most values cluster around 0. This is perfect for illustrating distribution. 2. The role of bins. The core concept of a histogram is the bin. The range of the data is divided into intervals or bins. The height of each bar in the histogram represents the count, the frequency, of data points that fall into that specific bin interval. The number of bins directly controls the shape and detail of the resulting plot. 3. Generating the histogram. We generate the histogram by calling plt.hist and passing our data array. By default, Matplotlib will choose an optimal number of bins, typically 10, for the visualization. We add a color and alpha for better visual appeal. Running this shows the classic bell curve shape of the normal distribution. 4. Customizing the number of bins. If the default setting lacks detail, we can specify the exact number of bins using the bins argument. Setting bins to 50 provides much finer resolution, revealing more minor fluctuations in the data distribution. Choosing the right number of bins is a balance between smoothing out noise and retaining important details. To summarize, histograms are essential for understanding data shape. Our next lecture 37.09, Plotting Subplots. See you there. Welcome back. This is the final lecture in our Matplotlib section. Until now, we have plotted only one chart per figure. However, a common requirement in data analysis is to show several related visualizations side by side. Matplotlib provides the plt.subplot function for precisely this purpose, allowing us to create multiple plotting areas, called axes, within a single figure. 1. Understanding subplots. When you plot in Matplotlib, you are always plotting on an axis object which lives inside a figure object. The plt.subplot function allows you to define a grid layout for these axes. The function takes 3 integer arguments: the total number of rows, the total number of columns in the grid, and the plot number that you are currently activating. 2. Setting up the plotting grid. We first prepare our data, 3 different Y arrays based on the same X values. We want to display these 3 plots in a single figure using a 2x2 grid layout, which gives us 4 potential slots. Three. Plotting the first 3 subplots. We call plt.subplot before each plot. For the first plot, we use plt.subplot 2, 2, 1, meaning a 2x2 grid, activating the first position. Any subsequent plotting functions, like plt.plot or plt.title, will target that active subplot. We repeat this process for positions 2 and 3. Notice that we use the shorthand notation to set color and line style simultaneously. Four. Displaying the composite figure. Finally, we use plt.tight_layout to automatically adjust the spacing between subplots, ensuring titles and labels don't overlap. Then, plt.show displays the figure containing all 3 separate, labeled plots. To summarize, subplots are essential for comparative visualization. This completes our Matplotlib section. You now know how to analyze data with Pandas and visualize it with Matplotlib. Our next section is in built data structures, starting with lecture 38.01, Introduction. See you there. Welcome to a new and important section of the course, Inbuilt Data Structures. Data structures are fundamental concepts in computer science. They are organized ways of storing and managing data so that it can be accessed and modified efficiently. In Python, several specialized data structures are readily available for specific use cases, and we will begin with the Q module. 1. What are data structures? A data structure is not just a container for data, but a container organized with a specific set of rules. For example, the Python list is a simple, general-purpose structure. But when we need to ensure that data is processed in a strict order, like handling print jobs or customer service requests, we need specialized structures like queues or stacks. 2. Python's Q module. For implementing classic data structures, Python provides the Q module. Although it is named Q, this module actually contains 3 different classes for handling ordered data, which we will explore in the coming lectures. Importantly, these classes are thread-safe, meaning they are designed to work reliably in concurrent environments where multiple parts of the program might access the structure at the same time. 3. Focus. The queue structure, FIFO. Our main focus will be the classic queue data structure, which operates on the principle of FIFO first in, first out. This means the first element added to the queue is always the first one to be removed. Think of a real-life queue at a checkout counter. The person who arrived first is the first person to be served. This strict ordering is critical for tasks like task scheduling and buffering. To summarize, data structures are essential for ordered data management. Our next lecture 38.02. Queue. See you there. Welcome back. In this lecture, we start working with the primary data structure in the queue module, the FIFO queue, implemented by the queue class. We will cover the two fundamental operations for any queue, adding items to the back and removing items from the front. 1. Creating a queue object. First, we import the queue module. Then, we instantiate the queue class to create our task_queue object. By default, this queue is boundless. It can hold an unlimited number of items. We will see how to limit its size later. 2. Adding items, the put method. The method used to add an item to the queue is called put. In queue terminology, this is known as enqueuing. We add a number, a string, and a list to demonstrate that the queue can store any type of Python object. All items are added to the back of the line. 3. Removing items, the get method. To retrieve and remove an item from the queue, we use the get method, known as dequeuing. Because this is a FIFO queue, when we call get, it always removes the item that has been in the queue the longest, the one at the front. The output confirms this. The number 101, which was put first, is retrieved first, followed by the string analyzed data. To summarize, put and get are the core methods for FIFO queues. Next, we will explore other essential methods for checking the size and status of the queue. Our next lecture 38.03. More queue methods. See you there. Welcome back. In the previous lecture, we learned how to add and remove items from a FIFO queue using put and get. In this lecture, we will cover the essential methods for inspecting the queue state, checking its size, if it is empty, or if it is full, all crucial for building robust, reliable programs. 1. Checking queue size. The queue size method returns the current number of items held in the queue. This is a simple but vital method for monitoring the workload, especially in producer-consumer scenarios where one part of the program adds items and another removes them. 2. Checking status. The empty method returns true if the queue contains 0 items and false otherwise. This is often used to prevent calling get on an empty queue, which can cause the program to hang. The full method returns true if the queue is at its maximum capacity. Since our current queue is unbounded, full will always return false. 3. Creating a bounded queue. To make the queue have a limited capacity, you must pass the max size argument during instantiation. Here, we set the maximum size to 3. Once 3 items are added, the queue is considered full. If you attempt to call put on a full bounded queue, the function will block indefinitely until space is available. To summarize, these inspection methods are vital for controlling data flow and preventing unexpected program halts. Our next lecture 38.04, LIFO queue. See you there. Welcome to our final lecture on the queue module. We have covered the FIFO queue. Now we explore the LIFO queue, which stands for last in, first out. This structure is more commonly known in computer science as a stack. The Python queue module provides the LIFO queue class for implementing this behavior. 1. Understanding LIFO. The LIFO principle means the last element added to the structure is the first one to be removed. Think of a stack of plates. You always take the top plate, which was the last one put on the stack. Stacks are fundamental for tasks like managing function calls, which is often called the call stack, and for undo mechanisms. 2. Creating a LIFO queue object. We create an instance of the LIFO queue class. Note that LIFO queues, like the standard FIFO queue, also support the max size argument for creating a bounded structure, although here we keep it unbounded. 3. Testing LIFO behavior. We use the same put and get methods as the FIFO queue, but the internal logic is different. We put items in the order 1, 2, 3. When we call get, the output confirms that action 3, delete, which was the last item put in, is the first item retrieved. This reversal of order is the definition of LIFO or stack behavior. To summarize, LIFO queues are ideal for processes requiring reverse order access. This concludes our module on inbuilt data structures. Our next section is encapsulation using decorators, starting with lecture 39.01. Introduction. See you there. Welcome to a new advanced Python topic, encapsulation using decorators. Encapsulation is one of the core principles of object-oriented programming. It means bundling data and the methods that operate on that data into a single unit, and, crucially, restricting direct access to some of the object's components. 1. The need for encapsulation. Consider this simple class. The age attribute can be directly modified from outside the class. This poses a problem because there is no built-in control, allowing us to set an invalid state such as a negative age. Encapsulation aims to prevent this direct, uncontrolled access and enforce data validity. Two, getters and setters. Traditionally, in object-oriented programming, encapsulation is achieved using private attributes and public methods called getters and setters. A getter retrieves the attribute's value, and a setter method sets the value, often including validation logic to ensure the value is valid before assignment. 3. The Pythonic way, the property decorator. Python offers a much cleaner, Pythonic way to achieve this using the property decorator. The property decorator allows a method to be accessed like an attribute. This lets us use a getter method without changing the client code from using dot notation. We use a leading underscore, like _age, as a convention to mark an attribute as intended to be private and not directly accessed. To summarize, the property decorator is key to clean encapsulation in Python. Our next lecture 39.02, Setter and Getters. See you there. Welcome back. In the last lecture, we introduced the concept of encapsulation and saw how the @property decorator could create a getter method. Now, we will complete the encapsulation process by adding a setter method, which allows us to control and validate how the attribute is modified. 1. Defining the property. We start by defining the getter method, which is named after the public attribute we want to expose, scorg. We apply the @property decorator to this method. Notice that inside the init method, we initialize the value to the private convention variable _score. Two, implementing the setter method. To enable setting the attribute using dot notation, we define a second method with the exact same name, score. We decorate this method with @score.setter. This ties the setter method to the existing getter. The setter method must accept two arguments, self and the new _score being assigned. Inside, we implement our core encapsulation purpose, validation. We ensure the score is within the valid range of 0 to 100 before updating the private attribute, or we raise an error. Three, testing the encapsulation. When we access student.score to read the value, the getter method is invisibly executed. When we use the assignment operator like student.score equals 95, the setter method is executed, validating the score before assignment. If we try to assign 150, the setter's validation logic catches the invalid value and raises the value error, protecting the object's integrity. To summarize, setters and getters using decorators provide controlled attribute access. Our next lecture 39.03, Delete Decorator. See you there. Welcome back. We have learned the getter and setter methods using property decorators. The final piece of the property puzzle is the deleter. The deleter allows us to intercept and control what happens when a user attempts to delete an attribute using the built-in Python del keyword, providing complete control over the attribute's lifecycle. 1. Review, getter and setter setup. We start with a class containing a property called salary, complete with a getter and a setter for validation. Now, we want to prevent or control what happens when a user calls del employee.salary. If we did not define a deleter, the default behavior would simply remove the attribute. 2. Implementing the deleter method. We define a third method, also named salary, and decorate it with @salary.deleter. This method takes only the self argument. Inside this method, we can place any logic we need. For example, we might log the deletion, perform cleanup tasks, or, as shown here, prevent the deletion entirely based on a business rule, like preventing salary deletion if the salary is below 1,000. If the deletion is allowed, we explicitly call del on the private backing attribute _salary. Three. Testing deletion control. We create two employees with different salaries. When we call del emp1.salary, the deleter runs, passes the check, and removes the private attribute. However, when we try to delete emp2.salary, the deleter's logic intervenes, prints the error message, and the del command for the private attribute is skipped, meaning the attribute remains intact. To summarize, the deleter provides crucial control over the final state of an attribute. Our next lecture 39.04, Delete Attribute. See you there. Welcome back. In our final encapsulation lecture, we examine the consequences of successfully deleting a controlled attribute using the deleter method. Understanding how Python handles attribute access after deletion is crucial for error prevention and maintaining code stability. 1. Class setup with deleter. We reuse the property structure, focusing on the name attribute. The deleter method's job is straightforward: log the action, and then use the del keyword to remove the private backing attribute _name from the object's dictionary. Two. Deleting the attribute. We create an instance and confirm its initial state. When we execute del product.name, the name.deleter method is called. This successfully removes the underlying _name attribute from the product object. Three. Consequence, attribute error. The most important result is what happens next. If we try to read product.name again, the getter method is executed. The getter, however, tries to return the value of self._name. Since that attribute was explicitly deleted, Python raises an attribute error, indicating the object no longer possesses the property. You must wrap such access attempts in a try except block if the attribute might have been deleted. To summarize, property decorators, getter, setter, and deleter, give you total control over attribute access, modification, and removal. This concludes our section on encapsulation. Next, we will move on to working with the JSON data format in Python. Our next section is using the JSON module, starting with lecture 40.01, Introduction. See you there. Welcome to a new section focusing on data serialization and transfer using the JSON module. JSON, which stands for JavaScript Object Notation, is a common format used for transmitting data between a server and a web application. Its human-readable, text-based format makes it indispensable for modern programming. 1. What is JSON? JSON is a lightweight data interchange format. It is essentially text organized as key-value pairs, very similar to Python dictionaries. Because it is language-independent, it is used everywhere to exchange data between different programming languages. 2. Python's JSON module. The standard JSON module in Python provides all the necessary tools to work with JSON data. Crucially, JSON data, when received or read, is initially just a string of characters in Python. We need the JSON module to convert this string into usable Python objects like dictionaries or lists. 3. Serialization and deserialization. There are two core concepts in this process. First, serialization converts a Python object like a dictionary into a JSON formatted string. In Python, this is called dumping the data, often done with json.dumps. Second, deserialization converts a JSON formatted string back into a Python object, which is called loading the data, done with json.load. 4. Python to JSON type mapping. It is important to know which Python types map to which JSON types. Python dictionaries become JSON objects. Lists and tuples become JSON arrays. Simple data types like strings and numbers convert directly, and Python's none becomes the JSON null keyword. To summarize, the JSON module is essential for working with web data. Next, we will use json.loads to parse a JSON string into a usable Python dictionary. Our next lecture 40.02, Parse JSON. See you there. Welcome back. In this lecture, we perform the crucial task of deserialization, converting raw JSON text into usable Python objects. We will use the json.loads function, where the S stands for string, indicating that we are loading data from a string. 1. Preparing the JSON string. We import the JSON module and define a string that holds our JSON data. This string could represent data received from a web API or read from a file. Notice that, in Python, this JSON is just a plain str type which cannot be accessed by keys like a dictionary. Two. Parsing the string using json.loads. We pass the JSON string directly into json.loads. The function automatically converts the JSON object notation into a native Python dictionary. The type of Python_data is now dict, making it fully functional for Python operations. Three. Accessing and modifying data. Since Python_data is now a dictionary, we can access its values using familiar dictionary key notation, like grabbing the version. We can also modify the data, just as we would any standard Python object, changing the version number or appending a new string to the tags list. This is the whole point of deserialization, making the data natively accessible. To summarize, json.loads is your tool for turning JSON text into usable data. Our next lecture 40.03, Parse JSON to file. See you there. Welcome to the final lecture in our JSON module. We have learned how to load JSON from a string. Now, we cover the reverse process, serialization or dumping, where we convert a Python dictionary or list into JSON format and write it directly to a file using the json.dump function. 1. Preparing Python data. We start with a standard Python dictionary, project_setting, which contains nested dictionaries, numbers, strings, and even the Python none value. This object is what we want to serialize and save. 2. Dumping data to a file. The core function is json.dump. Unlike json.dumps, which returns a string, json.dump takes two required arguments: the Python object to be dumped, which is project_settings, and the file object where the data should be written, which is f in our with block. This writes the entire JSON data structure to the settings.json file in a compact, single line. 3. Pretty printing with indent. While the compact JSON is machine efficient, it is hard for humans to read. We can format the output using the optional indent argument. By setting indent to 4, Python adds 4 spaces of indentation for each level of nesting, making the output file much more structured and readable for debugging or configuration purposes. To summarize, json.dump is how you write Python data to disk in the universal JSON format. This concludes our JSON section. Next, we will begin our introduction to the modern data application framework, Streamlit. Our next section is Introduction to Streamlit, starting with Lecture 41.01. Introduction. See you there. Welcome to a completely new and exciting section. Introduction to Streamlit. Streamlit is a modern, open-source Python framework that allows data scientists and machine learning engineers to create beautiful, interactive web applications for their data projects with minimal effort and without needing any web development experience. 1. What is Streamlit? Streamlit is specifically designed to turn data scripts into shareable web apps. Instead of writing separate code for the backend logic and the front-end user interface, Streamlit lets you write everything in pure Python. It handles the complex plumbing of web development for you, allowing you to focus purely on your data and models. 2. Why use Streamlit? Streamlit solves the problem of sharing dynamic data results. Historically, if a data scientist wanted to let a colleague interact with a model or filter a large dataset, they had to build a full web application using complex frameworks like Flask or Django, requiring knowledge of HTML, CSS, and JavaScript. Streamlit replaces all of that with simple Python function calls. 3. The execution model data flow. A key concept in Streamlit is its unique data flow. Whenever a user interacts with a widget, like a slider or a button, Streamlit automatically reruns the entire Python script from top to bottom. This reactive, single-page execution model is what makes it so simple. It is Python first. The code you write is the app you get. To summarize, Streamlit is designed for speed and simplicity. Our next lecture 41.02, Project Setup. See you there. Welcome back. Before we can start building interactive apps, we need to set up our environment. This lecture covers the essential steps: installing the Streamlit library and learning the specific command required to run a Streamlit application. 1. Installation using pip3. Since Streamlit is a pure Python library, installation is straightforward using the pip3 package manager. Simply open your terminal or command prompt and run pip3 install Streamlit. This command fetches and installs the library and all its dependencies. 2. Creating the app file. All Streamlit applications are simply Python files. Create a new file. Let's call it first_app.py. Inside, we import the library, typically aliased as stk. Then we call a simple function like st.title to display text, which will serve as the initial content of our application. Three. Running the Streamlit app. To launch the application, you must use the Streamlit run command followed by the name of your Python script. Execute this command in the same directory where your script is saved. Streamlit will automatically open a new tab in your web browser, usually at a local address like localhost port 8501, displaying your running application. 4. The Streamlit local URL. When the app launches, the terminal will display two URLs: the local URL for access on your machine, and the network URL for others on the same network. Your app will be running at one of these addresses, ready for interaction. To summarize, the setup is quick and simple. Our next lecture 41.03, Hello Streamlit. See you there. Welcome back. Now that our project is set up, let's explore the core function Streamlit provides for displaying content. In this lecture, we will learn how to write titles, headers, standard text, and data using just a few simple Streamlit commands. 1. Writing the Streamlit script. We start a new file, app.py, and import Streamlit as stl. We also import Pandas, as we will use it soon to demonstrate how Streamlit handles data. 2. Displaying titles and headers. To add visual structure, Streamlit provides dedicated functions. st.title displays the largest, most prominent text for the page title. st.header and st.subheader display section headings, which are rendered with different font sizes and boldness. 3. Standard text and data. The most flexible function is st.write. If you pass it a string, it displays text. More importantly, if you pass it a complex object like a Pandas data frame, it automatically renders it in an attractive, interactive table format, demonstrating Streamlit's data focus. 4. Using Markdown. For fine-grained control over text formatting, the st.markdown function accepts Markdown syntax. This is highly useful for integrating bolding, italics, lists, and links without complex HTML. The combination of st.write and st.markdown covers almost all of your content display needs. To summarize, these simple commands are the building blocks of any Streamlit app. Our next lecture 41.04, Calculator. See you there. Welcome back. We are moving beyond displaying static content to creating interactive applications. In this lecture, we will build a simple two-number calculator to demonstrate how to capture user input using Streamlit widgets and how the framework's reactive execution model makes interaction seamless. 1. Capturing numerical input. We start with the st.number_input widget. This is designed for numerical values and returns the entered value, which we store in number1 and number2. When the user changes the value in the input box, Streamlit detects the change, and as we learned, it reruns the entire script, updating the variable with the new value. Two. Selecting the operation. Next, we use st.selectBox to let the user choose the arithmetic operation. This widget displays a drop-down list. The selected option, such as add, is stored as a string in the operation variable. Changing the selection also triggers a script rerun. 3. Performing the calculation and output. Since the entire script runs every time an input changes, we simply place our calculation logic after the input widgets. We use standard if-else conditions based on the selected operation. When the script runs, the calculation is performed using the latest values of number1 and number2. Finally, we use st.success to display the result prominently, providing immediate feedback to the user. To summarize, Streamlit handles the web complexity. You just write the Python logic. Our next lecture 41.05, Use data frames. See you there. Welcome back. Streamlit is a powerful tool for data scientists, and a core reason for that is its seamless integration with Pandas data frames. In this lecture, we explore the primary ways Streamlit displays tabular data, differentiating between interactive and static table visualization. 1. Creating sample data. We first set up a Pandas data frame using NumPy to generate some random numbers. This data frame, df, represents the kind of structured, tabular data often analyzed in data science projects. We want to display this data in our Streamlit app. Two. Interactive display, st.dataframe. The primary function for displaying dataframe s is st.dataframe. This function renders the data in a dynamic table. Users can typically scroll through large datasets, and depending on the Streamlit version and settings, they might be able to sort or resize columns. This function is preferred for presenting large datasets that users need to explore. Three, static display, st.table. In contrast, st.table displays data statically. It cannot scroll or interact. This function is optimized for displaying smaller datasets like configuration summaries or the head or tail of a data frame because it loads the entire dataset into the Document Object Model or DOM at once. To summarize, choose Data Frame for big data exploration and Table for small, fixed displays. Our next lecture 41.06, Feedback App. See you there. Welcome to our final lecture on the basics of Streamlit. We have covered displaying data and simple input. Now we will build a functional user feedback application, demonstrating how to use buttons to trigger actions and how to handle form submission in Streamlit. 1. Designing the input form. We use two different input widgets. First, st.slider is excellent for capturing a numerical range, here used for the user's rating from 1 to 5. Second, st.text_area is used for long, multi-line text input, perfect for comments. Both these actions automatically update their respective Python variables. Two, the submission button. We add an st.button. Crucially, when this button is clicked, it returns true and triggers the entire script to rerun. We store this Boolean result in the submitted variable. This is how we know the user is ready to finalize their input. 3. Handling submission logic. We wrap our form processing logic in an if submitted block. First, we perform a validation check, ensuring the comment length meets our minimum requirement. If the validation fails, we display an error using st.error. If successful, we display a confirmation message using st.success, including the captured data. In a real-world application, this is where your code would save the data to a file or database. To summarize, the combination of input widgets and reactive execution allows us to build powerful, full-featured applications easily. This concludes our introduction to Streamlit. Next, we will transition into data validation with the powerful Pydantic library. Our next section is using Pydantic for data validation, starting with lecture 42.01, Introduction. See you there. Welcome to a new and critical section on data handling, using Pydantic for data validation. In modern Python applications, data comes from external sources like APIs, JSON files, or forms. Ensuring this data is accurate and fits a predefined structure is paramount. Pydantic is the leading library for achieving robust data validation and settings management. 1. The need for data validation. When you receive data, say a user registration form, you must ensure the age is an integer, the email is a valid format, and the name is present. Without validation, incorrect data can crash your application or corrupt your database. Pydantic automatically performs these checks when data is loaded into a Pydantic model. 2. What is Pydantic? Pydantic is a library that uses Python type annotations to enforce data shape. It offers runtime type checking, meaning it validates the data when you create an object, not just when you define the class. It automatically converts data types where possible, like turning the string 10 into the integer 10, and raises clear errors when validation fails. 3. Pydantic models and type hinting. The foundation of Pydantic is the model, which is a class that inherits from base model. Inside this class, we define fields using standard Python type hints, str, int, bool, and so on. This simple definition tells Pydantic exactly what structure the data must have and what types are expected. Pydantic then enforces these types automatically. To summarize, Pydantic makes data validation clean and Pythonic. Our next lecture 42.02, Setup Project. See you there. Welcome back. To begin using Pydantic, we first need to set up our development environment. This lecture covers the simple installation process using pip3 and establishes the basic Python file structure we will use throughout this section. 1. Installing Pydantic. Pydantic is a third-party library, so we must install it using pip3. Open your terminal or command prompt and run pip3 install Pydantic. This command installs the core Pydantic library and its dependencies, making it available for use in your Python projects. 2. Setting up the project file. For our exercises, create a new Python file, perhaps called data_validation.py. The first step in any Pydantic script is importing the base model class, which is the foundation of all Pydantic data structures. We will then define our data models by inheriting from base model. 3. Pydantic's dependence on type hinting. Remember that Pydantic relies completely on Python's type hinting syntax. When defining fields in our models, we will rigorously use standard types like str, int, and float, as well as types from the built-in typing module, such as list and dict. A strong understanding of Python type hinting is key to using Pydantic effectively. To summarize, we are ready to define and test our first model. Our next lecture 42.03, Pydantic in action. See you there. Welcome back. Now that Pydantic is installed, let's see it in action. We will define a simple data model and test how Pydantic handles various types of input, focusing on two key behaviors: successful validation and automatic type coercion, and failure handling. 1. Defining the sensor reading model. We define a simple model that inherits from base model. It requires an integer ID, a floating point temperature, and a string status. Remember, by simply using type hints, we are defining our required data structure and validation rules. 2. Successful validation and coercion. First, we test with data that perfectly matches the types. This works instantly. Next, we test with data that requires type coercion. We pass strings where integers and floats are expected. Pydantic is smart. It sees 102 can be converted to an integer and 25 can be converted to a float. It performs these conversions automatically, and the resulting Pydantic object holds the correct native Python types. Three. Handling invalid data. If the input data is missing a required field, or if the type cannot be coerced, Pydantic raises a validation error. This error contains a clear list of all fields that failed validation and why. This is incredibly valuable because it tells you exactly what data to fix. We must always wrap Pydantic instantiation in a try except block to safely handle external, potentially invalid data. To summarize, Pydantic ensures data integrity at the entry point of your application. Our next lecture 42.04. Use optional. See you there. Welcome back. In the real world, data is rarely perfectly complete. Sometimes a field might be missing, but we still want the rest of the data to validate. In this lecture, we learn how to define optional fields in Pydantic models using the optional type, which allows a field to be present or safely omitted. 1. Defining optional fields. To make a field optional, we use the optional type, which must be imported from the typing module. Optional of string means the field can contain a string or it can be none. By setting an explicit default value, like equals null, we tell Pydantic that the field is not strictly required during initialization. Similarly, if we set a default value like equals false for is underscore premia, the field automatically becomes optional with that default value. 2. Using the optional union syntax. For those using Python 3.10 or newer, there is a cleaner way to define optional types using the pipe or union operator. Float pipe none means the field can be either a float or none. This is the preferred modern syntax and is functionally identical to optional of float. 3. Testing with missing fields. When we instantiate the customer model with only customer underscore ID, Pydantic successfully creates the object because the other two fields are optional. The phone underscore number defaults to none, and is underscore premium defaults to false. If we were to omit customer underscore ID, the model would fail validation, as it is a required field with no default value. To summarize, optional fields are essential for handling flexible or incomplete data structures. Our next lecture 42.05. Use constraints. See you there. Welcome back. Pydantic's power goes beyond simple type checking. In this lecture, we explore how to enforce specific constraints on values, such as ensuring an integer falls within a certain range or a string has a minimum length. This is achieved using Pydantic's built-in constraint types. 1. Constrained integer, conint. To ensure an integer field, like a rating, is within a specific boundary, we use conint. By setting gt equals 0 and le equals 10, we ensure the score must be greater than 0 and less than or equal to 10. If a number outside this range is provided, Pydantic immediately raises a validation error. 2. Constrained string, constr. For strings, the constr utility allows us to enforce rules like minimum and maximum length. Here, we set a min underscore length of 3. We also add strip underscore whitespace equals true, a powerful feature that cleans the string before validation, preventing users from submitting strings that are just spaces. 3. Testing constraints. We first confirm that valid data, like a score of 7, passes instantly. Then we test the boundaries. When we try to instantiate rating with a score of 11, Pydantic immediately checks the conint constraints, finds that it is not less than or equal to 10, and raises a precise validation error. Similarly, attempting to use a username that is too short triggers the constr error. To summarize, constraint types are vital for ensuring the quality of your data. Our next lecture 42.06, a commerce example. See you there. Welcome to the final lecture in our Pydantic section. We have covered models, optional fields, and constraints. Now, we will bring these concepts together to build a robust e-commerce product data model, simulating real-world data validation challenges. 1. Defining the e-commerce model. Our product model defines 4 fields, each with different validation rules. We use conint to limit the product underscore ID to a sensible range. We use conFloat to ensure the price is always greater than 0. The description is optional, defaulting to none. Finally, tags must be a list of strings. Two, successful validation. We test with data that omits the optional description and provides the product underscore ID as a string. Pydantic successfully coerces the ID to an integer and validates that the price is positive, creating the product1 object without errors. Three, handling multiple validation failures. Now we deliberately pass bad data. The ID is too large, the price is negative, and the required tags list is missing. When the validation error is raised, Pydantic strength is apparent. It aggregates all the failures into one detailed error list, showing which field failed, lock, and the specific reason, message, for each failure. This is extremely helpful for debugging and informing users or external APIs about data problems. To summarize, Pydantic is your shield against bad data, ensuring robust application logic. This concludes our section on Pydantic. Our next section is Wrap Up, starting with Lecture 43.01. Congratulations and thank you. See you there. Congratulations! You have completed the core content of this comprehensive Python programming course. Take a moment to acknowledge how much ground you have covered, from the very basics to advanced application development tools. This lecture is a quick summary of your journey and a thank you. 1. Reviewing your journey, Python fundamentals. We started with the Python basics, setting up your environment, understanding core data types like lists, tuples, and dictionaries, and learning control flow statements like if-else and loops. You then gain strong foundational skills in organizing code using functions, modules, and decorators. 2. Learning object-oriented programming. You successfully navigated the entire OOP paradigm, learning how to build complex, maintainable applications using classes, inheritance, polymorphism, and abstraction. These skills are essential for large-scale, enterprise-level programming. 3. Advanced application skills. Finally, you moved into practical, specialized areas. You learned how to handle errors gracefully with exception handling and logging. You gained knowledge with I/O operations, threads, networking, and vital data tools like SQL, MongoDB, and JSON parsing. 4. Data science and modern frameworks. The final modules equipped you with highly sought-after industry skills: data manipulation using NumPy and Pandas, data visualization with Matplotlib, fast application building with Streamlit, and robust data validation with Pydantic. These tools make you job-ready in the data domain. Your journey has just begun. Thank you for choosing this course. In the very next and final lecture, we have a small bonus to wrap up the course. Our final lecture, 43.02, bonus lecture. See you there. Welcome to our very last lecture. This is a short bonus session where we will share a quick, useful Python trick and leave you with some final thoughts on continuing your programming career. 1. Bonus tip: F-string debugging. You are already familiar with F-strings for simple formatting, but Python 3.8 introduced a powerful debugging feature. By adding an equal sign right after the variable name inside the curly braces, as in operator name equals, the F-string automatically includes the variable name, the equal sign, and its value in the output. This simple feature drastically improves print debugging speed. 2. Beyond the course, continuous learning. The programming world evolves quickly. Your first priority should be to build things. Nothing cements knowledge better than applying it. Create projects, even small ones, that force you to use the libraries we covered, like building a small Streamlit dashboard that fetches data using a Pydantic model. 3. The Python community. Python has one of the best communities in software development. Do not hesitate to engage. Read the official documentation, join forums like Stack Overflow, and explore open-source projects on GitHub. Learning to read other people's well-structured code is a rapid way to improve your own coding style. You have earned a solid foundation in Python. I hope you enjoyed the course, and I wish you the very best in your programming career. Thank you and goodbye. This concludes the course. Thank you for participating.